IP. Where do we find that? We find that at the internet layer of the TCP/IP model. We find it at layer 3, or the network layer of the OSI model. It's connectionless. Wait, connectionless. What do we mean by connectionless, Dan?
Well, you'll hear many people say many things about this one. But what it means is you can communicate without forming a conversation. When I do a ping, I might ping an IP address. That does not require a conversation to be formed. The contrast of that would be connection-oriented. And TCP, working at a layer above, at the transport layer, could give us connection-oriented services. But going back, connectionless means we don't have to do things like the three-way handshake. And when we communicate IP packets through an internetwork, each packet is treated independently. Routers don't naturally keep track of what they did in the past. They just care about the here and now. What does my routing table say to do right now? And I'm going to forward based on what the current routing table status is. So it is possible that our traffic will be rerouted. We're going to look at the structure of these IP addresses. There are two big parts. And because they have two different elements, one tells us where we are geographically in the grand scheme, and the other section tells us our unique identifier. That makes it hierarchical. Just like our phone numbers. One part tells us where we might live, where our phone number is based in, and then we have a unique identifier that sets us apart. Best effort delivery is kind of funny. It's almost a euphemism for saying no extra effort. We take a packet in, we route it, also called packet switching, and we don't really care afterwards. We do not have assured delivery, at least in terms of layer 3 of the OSI model as it pertains to IP. So there's no data recovery built in here, but there could be elsewhere at the transport layer with TCP. And we've already covered this one, network access. We abstract that section. We don't worry about it. We just say, give me something that I can work on top of, and I'll do the rest.
So there's a lot of different types of media that we can work on top of here. Copper, fiber, doesn't matter. We're not restricted to anything. And we'll find two variants of IP here at the internet layer. IP version 4 and IP version 6. We'll be talking about both IP version 4 and IP version 6 in this course. So let's get into our IP addresses. What do we use IP addresses for? We use them to identify our hosts and our devices on our networks.
Let's define that idea of host for a moment. I used to struggle with this. But host is anything that runs the TCP/IP suite. So it could be a PC, it could be a server, it could be a managed device via IP, such as a switch, which would consume a host address. So we think to ourselves, host, that sounds like client, sounds like a PC, but it really could be anything that runs the TCP/IP stack. So, Raymond, I need a host address in order to work with the TCP/IP suite.
Not only do you need it, it has to be unique. We can't have two devices with the exact same IP address. That would cause a conflict. Think about it this way. Your home has a unique address. It has a number associated with it on a specific street. Is there anybody else on that street that has the exact same number? No? You might be saying, what about an apartment complex? Well, wait a second. an apartment complex has a specific number on that street. And then inside of that apartment complex, we have 1A, B, C, D. Maybe that's the numbering inside that apartment complex. But on that street, that building is still uniquely identified. So in our networks, our IP networks, we have to uniquely identify all these different hosts. And we're going to have two portions to our IP address. We're going to have a network portion and a host portion. That network portion plays a very important role.
We've talked about broadcast domain for a moment. Talked about it earlier. And sure, yes, that's the place in which the region in which a broadcast will go. But the broadcast domain is the layer 2 space that would be associated with the layer 3 space of a network. So Raymond, if I'm in the same broadcast domain at layer 2, let's move up now. In the same broadcast domain, do I need to share the same network portion in order to be properly addressed at layer 3?
Most definitely. We all have to be in the same network. Just like your home and your neighbor's home are all on the same street. You share that same street. It's the same type of concept here. And then we have that host portion, which is that unique portion of that address that nobody can share. So we all belong to the same network, but we all have to be individually identified in that host portion. So just like our discussion of layer 2 and the frame format, we have to understand what's happening at layer 3. And at layer 3, we don't call it a frame. Do you remember what we call it at layer 3, this protocol data unit? What's the name of that? Let's run down through it. We have data, we have segments, we have packets, we have frames, we have bits. This is our packet. Specifically, we're looking at our packet header here, Dan.
And the very first field of the header is worthy of our discussion. Do you remember what the two versions of IP are? Raymond mentioned them earlier. Here we're looking at version 4. So that's one of the two. Then there's version 6. And let's just not worry about IPv5, which some people say never existed. Some people say it was basically a flash in the pan. But it's V4 and V6. Here, we're looking and squarely focused on IPv4. So although we mentioned that there's V6, that's for later. Our deep dive on V6 is for later. Every field in this header is not necessarily worthy of discussion, especially at this juncture. But let's go through the key ones that are good to know as a Cisco individual. So across the board, if you're a Cisco person, these are the good ones to know. Jump to service type. Service type has another name called TOS. TOS. Type of service. And Raymond, what sorts of things could we do with the type of service byte in the IP packet header?
We have the ability to discriminate against the different types of packets that are flowing through our environment. What do I mean by discriminate? Well, I could set priorities. I could state that this packet is more important than that packet. And this packet over here is way more important than that packet. That way there, when the packet arrives at the router knows who to give priority to and allow through the router first. This is very important when we're dealing with voice traffic versus data traffic. That voice traffic is very, very important. We want to minimize delay. We want to minimize latency. We have to get that voice traffic through the router as quickly as possible. So let's push all the other data aside, all those other packets aside, and allow the voice traffic to go through first. That's when we can use this service type field for or the type of service field for.
Now, Raymond and I are certainly capable of talking to things that we don't need to talk about. And we're going to use our judgment here, and we're going to jump down to time to live. You start to think packet length, identification, flag, fragmentation offset. Absolutely not worthy of our discussion here for CCNA or CCNP. So that's our litmus test. If we don't need to worry about it for CCNP, we're not going to talk about it here. Time to live. So Raymond's in his 30s, as am I. We've got a time to live of about, well, in Raymond's case, I'm putting him at about 20 years more. And me, much longer. Raymond, in terms of packets, how do we evaluate the time to live for packets, and how do we even measure this?
Well, we're going to have a starting value that is set. Typically, it's 255. And that value is going to decrement each and every single time a router forwards a packet. So let's say it's at 250 right now. The router receives the packet, forwards it, it's now 249, and so on and so forth. Why do we care about this time to live? Well, without this time to live, if this packet did not reach the destination, it would just keep going on forever and ever and ever. Do we want packets to go on forever and ever and ever? No, we don't. Not at all. We want them to eventually disappear if they don't reach their final destination. And that's what this time to live field gives us the ability to do.
Okay, so let's play a what-if scenario. Packet had to go from A to B, but it got caught in a loop, and it eventually gets its time to live down to 0. What then happens, Raymond, once that router decrements, goes from 1 down to 0, that very important number where we expire the packet, what do we then do?
That router is going to send a packet to the bit bucket. Bit bucket? Yeah, the garbage can. It's going to get rid of it. But it's also going to send a time exceeded message back to the source of the packet. And this is an ICMP message that goes back.
Pretty important field. IPv6 names that more appropriately, by the way, hop limit. Hop limit. That's a lot more accurate name. Now, the next one is protocol, and we start to think to ourselves, well, I know this is the IP packet, so the protocol is IP, right? Well, that was specified in the very first field. IPv4 is version. So then, why do we have another protocol field yet again inside of it? One identifies that I'm v4, but the protocol ID field identifies what transport layer protocol or protocol that is next up the OSI model that we are going to decapsulate to. Very important. So we're at layer 3 of the OSI model. The layer above that the protocol ID points to is a transport layer protocol. TCP and UDP, they would be encoded here. It's one or the other. That's very, very important. But let's not lose sight of why we're here. We've already done that. But the time that we spent here gave you some good exposure. But we're talking about IPv4 addresses, Raymond. And what could we glean inside of the packet header about these v4 addresses?
Well, inside of our packet header, we'll find both the source and destination IP address. We can see fields specific to those addresses. But I want everybody to notice something, and that is the size of our IP version 4 addresses. Look at the very top. We see byte 1, byte 2, byte 3, byte 4. And if you recall back from our discussion on frames, we said that a byte contains 8 bits. So if I have 4 bytes, I would have 32 bits. And if I look down at my source and destination address, they're both 32 2 bits long. How do we know the source address? It's my source address. That's me. It's the sending device. How do we know the destination address? We're either going to know it specifically, or we'll know it by name. Think about when you type in www.cisco.com. You're typing in the name. And then there's a service running in the background that's going to get the destination IP address for you. What is that service, Dan, we're talking about?
DNS. The DNS service is going to give us the ability to resolve a fully qualified domain name, what are those web addresses, to something we can tuck inside of the packet header. We can't put in the destination www.anything or anything.com or .edu or .gov or .ca. Nope. We have to put in an IP address. So we cannot circumvent the mechanisms that were designed for us. If I communicate a packet, I have to have an IP address for the source and an IP address for the destination.
Do we see 192.168.1.1 in our fields here for our packet header? No. We see decimal. We see binary values. Not decimal values, binary values.
I don't see anything, Raymond.
So we have to have an understanding that our devices are communicating using ones and zeros.